Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this scribblecast lecture, we're continuing with our study of derivatives of carboxylic acids, looking at the last of the carboxylic acids and the most unique, nitriles. Nitriles are the only carboxylic acid derivative that lack the C double bond O or carbonyl group. Nitriles are carboxylic acid derivatives that consist of a C triple bond N, the C triple bond N or cyanide functional group. They're sometimes called cyano compounds or cyanides. Let's begin with the nomenclature of nitriles. Okay, so nomenclature. IUPAC nomenclature for the molecules are named as alkane nitriles. If the cyclic ring possesses a nitrile, the oxalic acid ending of the carboxylic acid is replaced by nitrile. Let's look at some examples for IUPAC name. Notice you must count all of the carbons, including the carbon of the triple bond N. So in IUPAC nomenclature, two carbon chains in ethane, this is an ethane nitrile. Now note the nomenclature for a ring containing a carboxylic acid, such as this guy. Okay. This molecule is named as a cyclohexane carboxylic acid. When you have a ring carboxylic acid that is replaced with a C triple bond N, the cyclohexane carboxylic acid, the oxalic acid ending is dropped, and you end up with a cyclohexane carbonitrile. So note the distinction between naming nitrile groups off of straight chains and nitrile groups off rings. Common nomenclature is to replace the ic acid with the word nitrile. However, if the root lacks the letter O, O is often added in between the dropped ic acid and nitrile. For example, the common name for 2-carbon carboxylic acid is acetic acid. If I just dropped ic acid, I'd have acetonitrile. But the actual common name is acetonitrile. So if O's already there, you leave it. But if there is no O, you drop ic acid and you add O-nitrile. Okay? Acetonitrile is the common name. Take, for example, the common name of the 3-carbon chain. 3-carbon chain IUPAC would be propane nitrile. It's pretty easy, one word, propane nitrile. But the 3-carbon carboxylic acid is propionic acid. So when you drop ic acid, you have propio left. The O's already there. So you don't put two O's. Okay, it's propionitrile is the common name. Now, when acting as a substituent, if there's a higher priority group on the ring, carboxylic acid is higher priority than cyanide. The substituent name for a C triple bond N is a cyano group. Cyano. And so in IUPAC, this would be 4-cyano benzene carboxylic acid. Note, I'm giving the literal IUPAC name. I know benzoic acid has been accepted by IUPAC and is used in preference to this. You could say 4-cyanobenzoic acid as well. Or in common nomenclature, you might say para-cyanobenzoic acid. Okay? So, note 4-cyanobenzoic acid is also correct. Okay. How do we prepare nitriles? Well, in all of our chemistry we've covered in the past year, we have come across only one preparation of nitriles that does not involve nucleophilic substitution. So let's take a look first at the nucleophilic substitution of alkyl halides. I can take, okay, so this is preparation of nitriles. I can take an alkyl halide, such as bromo, 1-bromopropane. I can react it with C triple bond N minus. Cyanide. Cyanide's a powerful nucleophile. Primary alkyl halide will go SN2. This reaction goes very well. And I will produce, well, can you name the nitrile that's been produced? Give me an IUPAC name. That's right. Butane nitrile. Now, if I have a 4-carbon carboxylic acid, if this was a C double bond OH, what's the common name? The common name of a CO2H with 4 carbons is butyric acid. Drop ic acid, add O nitrile. I get butyro nitrile. Okay, so very good methodology for preparing nitriles. Now, I said there was one other reaction we covered. Do you recall what that reaction is? If you came up with diazonium salt chemistry from last semester, you have a good memory. Diazonium salts can be prepared and converted to benzene nitriles, benzene-based nitriles. Diazonium salts, remember it, are prepared from aniline. Aniline is an aromatic ring with an NH2 off of it. And we'll be looking at this a little more closely when we get to amine chemistry. If we react this with sodium nitrite in 2 HCl's at 0 degrees C, we can make benzene diazonium chloride. Benzene diazonium chloride. Now, benzene diazonium chloride is an N triple bond N, which is a very good leaving group, attached to the ring, Cl minus. One of the reactions we learned regarding benzenediazonium chloride was reaction of CuCN with copper CN. CuCN, copper CN with the diazonium salt. If you do this reaction, you will produce benzonitrile. Common name benzonitrile, IUPAC, benzene carbonitrile from benzene carboxylic acid. Benzonitrile, because it's based on benzoic acid, is accepted by IUPAC. So if you like, just benzonitrile is fine. That's either IUPAC or common in this case. So you either say benzonitrile or benzene carbonitrile from benzene carboxylic acid. That's it for the preparation of nitriles. Two basic preps, both work reasonably well. One for making aromatic-based cyano groups, and the other for making alkane-based cyano groups. Let's take a look at now the reactivity of nitriles. Well, all the reactivity is obviously going to be based on the RC triple bond N group. Okay. Now the triple bond has pi and sigma components with a lone pair of electrons. In terms of basicity, the lone pair of the nitrile is not very basic. It's an sp orbital. Compared to sp squared and sp cubed, there's a much greater s character, which means the orbital is much smaller, held closer to the nucleus. It's like the nitrogen is more electronegative. It's less available for protonation. Typical pKb is a very large number, meaning it's quite low basicity. It's usually around approximately 24. The lone pair is less available to protonation because it lies close to the nucleus. However, nevertheless, nitriles are carboxylic acid derivatives. In that case, that means you can react them with water, either in base or acid, and produce, you should be able to produce carboxylic acid. If that is the case, we need to know how it can happen. So let's take a look at reactions of nitriles in base and then in acid. If we react in base, hydroxide, clearly nucleophilic attack will go for the carbon because the electronegative nitrogen, delta minus, withdraws electrons, putting a delta plus. And so our OH can attack the delta plus on the carbon. If this happens, to prevent 10 electrons being around carbon, we have to break a pi bond. We'll get an RCOH, double bond N. All right? And the nitrogen has a negative charge. Now, there are no protons around in the sense of free H+. And as a result, hydroxide, though, has to be dissolved in a solvent. And N- is sufficiently basic, even on an imine, to abstract proton from water and produce more OH-. So H2O comes in, produces the H-, and we get RCOH. Double bond, NH. We get what looks like an imine. Now, hydroxide certainly can come in again and grab a proton. So have OH minus come in and act as a base. This would make RC O minus. And it's easier to protonate rather than normal alcohol because of the pi bond to the nitrogen. The negative charge is resonance stabilized. Actually, let's draw it as resonance arrows might be a good idea. And so we have our NH, two lone pairs, negative charge here. C double bond O, R. And so we can have H2O come in again. And donate a proton. To the N. And you'll notice that part of the hydrolysis of a nitrile leads to what kind of functional group? An amide. We form an amide functional group. And so the next or rest of the procedure is just hydrolysis of the amide. The first step of hydrolysis leads to amide, and then the amide continues to react. Plus OH minus as a nucleophile. We get R, C, O minus. Get an OH. We have an NH2. And what happens when we kick this out? We can dump the electrons back in, kick out NH2. We get R, C, double bond O, OH, plus NH2 minus. Very, very quickly, this very powerful base will deprotonate the acid and you end up with RC double bond O, O minus and NH3. And under aqueous conditions, even in hydroxide, NH3 may go to NH4 plus, making ammonium hydroxide, because NH3 is a more powerful base than even hydroxide. Okay. This last step is very fast and irreversible. Once you get the carboxylate, it is a done reaction. A done deal. Okay. Very good. So that's the reaction in base. Let's take a look at the same hydrolysis reaction but this time in acid. Okay. And so we're going to have RC triple bond N. And obviously the first thing we can do is protonate the lone pair. Now I did indicate that it's not very basic, but under acidic conditions there will be an equilibrium with the protonated version. That protonated version will be resonance stabilized where the pi electrons move towards the nitrogen, producing a C double bond N, lone pair H, and the plus is now on carbon. It's a minor contributor, but we can then have water attack. Okay. Notice going backwards would be minus H plus here. Minus H2O would take us back. And we can attack the C plus. What that gives me is RCOOH, H, lone pair plus. There's a plus on this, and I have a double bond NH. Well, obviously, the first thing that can happen is I can lose a proton, minus H plus off the oxygen. Going back would be plus H plus. Minus H plus will give me an RCOH, double bond NH. We can now protonate the lone pair on the imine again, or on the nitrogen again, would be better to say. If we do that, we get RCOH, double bond NH2 positive. Well, clearly this is resonance stabilized. I guess I could actually draw 3 resonance contributors. So before we bring that lone pair in, let's draw this one. RCOH, NH2, lone pair, and a plus on carbon. If I dump the lone pair in, I now get R C double bond O H, one lone pair plus on oxygen, NH2. You notice that looks like a protonated amide. Indeed it is. If that resonance contributor loses H plus, minus H plus, plus H plus. So even in acid, you see we could very easily produce some amide. Okay. However, this resonance contributor, none of the contributors exist. There is a carbocation character to the carbonyl. Some water will be attracted to this, plus H2O. Minus H2O, which will give me an OH, C, OH, H, R, NH2, lone pair positive. Okay, next we take a proton and remove a proton, minus H plus, plus H plus, giving me R, C, OH, OH, and an NH2. The next step involves protonation of the NH2 lone pair, plus H plus, minus H plus. We have RCOH, OH. Protonation of the nitrogen leads to a better leaving group, NH3 plus. And if that nitrogen leaves, minus NH3. Notice the NH3 will very quickly convert to NH4 plus in acid. That will produce RCOH, OH, positive. Each oxygen has a lone pair it can dump in, so there are two resonance contributors for this. RC double bond OH, lone pair positive. OH. Actually, we might as well draw it this way now. And RCOH double bond OH positive. So what do we have? We have this resonance stabilized carbocation, which if we simply deprotonate, minus H plus H plus, we get to carboxylic acid. Some interesting points about this chemistry. First off, it goes through amide formation, so there will be some concentration of amide solution. The first few steps involve protonation and conversion towards amide. Amide is part of this resonance stabilization of this carbocation. Once water attacks, we protonate the nitrogen to get a good leaving group, but note the NH3 is sufficiently basic that it will very quickly in acid be protonated to NH4 plus. So there you have it. Nitrile is a carboxylic acid derivative because it reacts in acid or base to give you carboxylic acid. Note the reaction mechanism in acid is a series of protonation and deprotonations to give you carboxylic acids with a few resonance structures. Looks complicated, but it's quite systematic if you look at it carefully. You systematically remove and add protons. Well, there's one other reaction we want to look at for nitriles. And that reaction is reduction. Now, like carboxylic acids, to be reduced, nitriles require fairly harsh conditions. But they can be reduced via catalytic or metal hydride reduction. For that reason, there are two pathways for reducing a nitrile to a benzylamine. The first I said was catalytic hydrogenation. That is, you take H2 gas in the presence of a metal catalyst. And that metal catalyst can be nickel, can be platinum, can be palladium. Let's use nickel. And you apply heat, sometimes even a low pressure. And the hydrogenation to the benzylamine will take place. Nitriles, like carboxylic acids, do require powerful reducing agents. So if you use a metal hydride, you must use lithium aluminum hydride. Of course, it's an ether. And react that. If you want an amine, don't use acid. You'll protonate the lone pair. So water is the most you can use. And you'll get to ammonia. Metal hydrides add H minus to the carbonyl. So the step 1 will put the H's on the carbon. It is the second step, water, which reacts with the aluminum nitrogen bonds to make the protons on the nitrogen. So H minus goes on carbon, protons from step 2 go on nitrogen, and you get the benzylamine. In the catalytic hydrogenation, the H2 gas's bond is activated by the metal surface, and it reacts to add across the pi bond. Okay, well that's it for the reactivity of nitriles, and that pretty much wraps up our discussion of carboxylic acid derivatives. In the next Scribblecast lecture, we're going to shift gears and start looking a little more closely at enolate and carbanion chemistry for carboxylic acids. We examined some of this chemistry in aldehydes and ketones, and so we're basically going to review all our knowledge of carbanions and show how carboxylic acid chemistry is involved, and carboxylic acid derivatives are involved in carbanion formation, and some of the interesting reaction mechanisms that come out of those structures. Well, I'm Dr. Brian Lloyd. This is my Scribblecast. I thank you for listening. This was a bit shorter one. Thank you very much.